an example of how we approach these type of questions and problems we're presented with. If, for example, we have a liquid which we supply with 220 joules of heat. You can also note that the units for heat are joules, so that links back to energy from last week. But anyway, we supply 220 joules to this liquid, and then we observe a temperature change of 20 degrees Celsius to 32 degrees Celsius. And so from this, we would, for example, note that the heat capacity, so we're not yet talking specific heat capacity, just a general heat capacity, is equal to the energy supplied, 220 joules, divided by the change in temperature, which will then, when we work this out, equal 220 divided by 12, which will then equal 18.3. And at this point, we're still not talking specific heat capacity, but we are able to actually assign units to this equation, which would be joules per Kelvin. But of course, we really need to work out specific heat capacities, as we have no idea what amount of liquid is being used. It could be a liter, could be many liters, could be a mil. We have no idea. So from this, the question then continues to state that the density of the liquid is 1 kilogram per cubic decimeters, and 10 mil was used in this experiment. And so from that, we are then able to calculate a specific heat capacity for this whole experiment. And within these type of problems and questions, it's always a good idea to keep in mind what you're trying to work out, and also keep in mind the units of everything. So we know we need to work out the mass of this liquid which was in this experiment to get a specific heat capacity. We've been given the density of the liquid and the volume. And if you can see, density, the units are mass per volume. So if we're to multiply mass per volume, kilogram per cubic decimeter, if we multiply that by volume, if it was in cubic decimeters, these would cancel, and it would therefore equal the mass. So to work out the mass of the liquid involved, we need to multiply these two numbers together. We also know we are going to need the mass of this liquid in grams. So we can work it out in kilograms first and then convert it to grams. And by doing so, if we first of all change mils into liters, which is equivalent to cubic decimeters, we can then work the mass of this liquid out as being equal to the density 1 multiplied by the volume in liters as 0.01, which will then give us a mass of this liquid being 0.01 kilograms or 10 grams. And so from this, we now have everything we need to work out the specific heat capacity. We have the heat, which is 220 joules, the change in temperature, which is the difference between the final temperature of 32 and the initial temperature of 20. And we've also just worked out the mass, which in this case we want in grams, which is 10 grams. And just to carry this through to show how we would do this sort of neatly and tidily, just plugging these numbers in, you can see the specific heat capacity of this liquid is then equal to 220 divided by 10, so 10 grams, multiplied by the temperature difference, which would then be equal to 1.83 joules per kilogram per gram. So now to hand it over to you to have a look at one of these. This time we're looking not at a liquid, but at a solid. So if the specific heat capacity of copper is given as 0.386 joules per gram per Kelvin, calculate the heat change when 13 grams of copper is supplied with 400 joules of heat. And just in case there is confusion, I am swapping between Kelvin and Celsius, but of course, 1 degree Celsius is equal to 1 degree Kelvin. And because we're looking at delta T, the change in temperature is therefore the same. Getting some answers coming in. Kieran's a maybe. Bit more sure now. And so, yeah, that looks great. So just to go through the calculations, we are using, let's go. Right, that's weird. So as we have seen, the specific heat capacity is equal to Q divided by M delta T. We can then rearrange that as we wish to work out the heat change, which is delta T. And so moving delta T up to the left-hand side, multiplying both sides by delta T, dividing by the specific heat capacity, we then arrive at delta T being equal to Q divided by M multiplied by the specific heat capacity. Putting in these numbers, this is then equal to 400 divided by 13 multiplied by 0.386, which ultimately is 78.7. So I believe you have better answers than me, as I seem to have got that very slightly wrong, but we'll round up to 18 and then everyone's right. Just to state, we also wanted units. It would be either Kelvin or Celsius. So 79.7 Kelvin. Next, if we were to do exactly the same, but this time to 13 grams of aluminium, which now has a specific heat capacity of 0.9 joules per gram per Kelvin, what would the temperature change be? So everything else is the same. The heat supplied is still 400 joules, and it's still 13 grams, but this time it is now aluminium. And as answers have come flying in, that is exactly it. So we can put the same numbers in, this time looking at aluminium, so different specific heat capacity. The things I wished to draw to your attention were that because aluminium has a larger specific heat capacity, this means the change in temperature is now smaller. Because, of course, specific heat capacity and the change in temperature are inversely proportional. Cool. Okay. Moving on to another one. This time we have a liquid question. And now we're given the specific heat capacity of water, of liquid water, as 4.18 joules per gram per Kelvin. And the question wishes you to calculate the energy required to heat 1 mole of water from 25 to 90 degrees Celsius. The other bit of information we are given is that the molar mass of water is equal to 18.02 grams per mole.
So when you say that you use the amount of substance in moles, is that the molar mass of it, or is it the amount of moles that are there? So if you want to know 1 mole of water, is it the molar mass of water that you put in, or is it just the one?
So the specific heat capacity is heat capacity per mass. And we're told there's 1 mole of water. So knowing the molar mass, you're actually able to work out the mass of 1 mole of water.
All right, okay, I was looking at it wrong.
Yeah, so
the wrong equation.
Yeah, so it was a bit misleading because it featured the term mole. It was directing you away, but it is actually asking about the specific heat capacity, which is per mass. So I believe everyone has got this spot on. So this is, of course, rearranging specific heat capacity, but this time we want to find the energy Q. We then had to work out the mass of 1 mole of water. As we know, there's 1 mole of it. The molar mass is 18.02 grams per mole. Therefore, 1 mole is 18.02 grams. Then it's just a case of putting these numbers into this rearranged equation to arrive at the final answer of 4896 joules, which everyone got perfectly. And then final one of these questions for today. Now we're going to look at mercury, which is possibly one of the coolest elements. So the specific heat capacity of mercury is 0.14 joules per gram per Kelvin. So if you can calculate the energy required to heat 5 mils of mercury from 10 to 120 degrees Celsius. We're again dealing with a liquid, and this time we're told the density of mercury is 13.6 grams per mil. So I think most of the answers are in, if not all of them. And I believe everyone similarly was able to rearrange this equation in the same way. And then if we have the density as 13.6 grams per mil, if you multiply that by a volume, which is also in mil, you will be left with the mass of that volume in grams. So the mass of mercury in this case, 5 mils of mercury, is equal to the density 13.6 multiplied by 5, so is 68 grams. This then can be entered within the rearranged equation, giving you a final quantity of heat, Q, as 1047 joules. So I think we've definitely covered that aspect of this week.